Good morning to all. I welcome you all for the session 2 of day 2 of this FTP. Let me give a short introduction about the speaker. The speaker of this session is Alex Noel Joseph Raj. He received his B degree in electrical engineering from Madras University in India in 2001, and he completed his ME degree in applied electronics from Anna University 2005 and PhD degree in engineering from the University of Warwick, Coventry, UK in 2009. From October 2009 to September 2011, he was with Wellport Limited Towns, UK as design engineer. From March 2013 to March 2017, he was with the Department of Embedded Technology, School of Electronics Engineering, VIT University. Since March 2017, he is with Department of Electronic Engineering, College of Engineering, Shantou University, China. His research interests include machine learning, signal and image processing, and FPGA implementations. He is specialized in image processing with industrial and teaching experience in machine learning, deep network signal and medical image processing, FGPA system design, MATLAB, Simulink, and so on. He is constantly looking for dynamic interns and postdocs. Totally, he has a teaching experience of 8 years and industry experience of 3.5 years. From Jan 2017 till date, he is working as professor in Department of Electronic Engineering at Shantou University, China. I now hand over to the speaker of the session.
Okay. So, very good morning. Thank you very much for this introduction. As the speaker just introduced me, I'm Dr. Alex Noel Joseph. So, currently, I'm a professor at the Shantou University, China. So, I thank the President Engineering College for giving me an opportunity to speak here. So, my topic of interest is going to be medical image segmentation using deep learning. So, am I clear? Am I audible? Can you just respond to me?
Yes, very much audible.
Yes, sir.
Great.
Yes, sir, you are audible.
Okay,
Fine,
so
sir.
I'm audible. Okay, great. So that's about me. Yeah. So the contents of this presentation. So I will start with about a very short introduction about computer vision. So what is computer vision? How it started off and all that stuff. Very simple explanation, not more than 2 slides. Then I'll speak about segmentation, types of segmentation, applications, and then I'll go into this CNN, which is also you can call it like deep learning or all that stuff. So the deep networks, so base segmentation. So we'll just know about what is convolution, pooling operation. Then I'll tell you about what are the problems with this normal CNNs, and why we need to go in for what is called as the upsampling. So after knowing this upsampling, then we will go into the unit architecture. So many of you would have come across this architecture called this unit. I've been working on this for quite some time with my master's student in Shantou. So we were working on some segmentation issues. So we were working on segmentation using ultrasound images. So I will show you, explain you about this unit and various examples of segmentation using this ultrasound images. So all done in our labs. Then I will concentrate on 2 models that we derived from this unit. So these are 2 variants, the RDA unit and RDA unit WGen. So these 2 variants were designed in our lab. So I will explain you about this. So in terms of the architecture, the outputs, and additionally, I will also get into this. This is like additional things. I will speak about a feature-based segmentation, maybe the retinal segmentation. Retinal, say you might know about this fundus images. So I will speak about how to use feature-based techniques to do this fundus segmentation. And finally, I will also speak about our interest in our work culture in aiding diagnostics. So basically, you want to work on image processing, signal processing in terms of medical diagnostics. So how we are able to help the doctors, the industry people from our labs. So I will also speak about this thing called aiding diagnostics. So few results I will show across as well. Okay, so this is the flow of my topics today. So you can note down the slide number or anything, and you can ask me questions at the end, or you can raise your hands. I think I'll just leave it to the moderator to decide which way we want to go through it. Okay. So about the presenter, that's me. So I have a PhD in engineering from the University of Warwick in UK. So it's one of the top 100 universities in the world. So I specialized in computer vision with FPGA implementations. So I was developing real-time depth estimations techniques, and I was developing the algorithm and implementing it on the FPGAs. So presently, I am a professor at the key laboratory of digital signal and image processing of the Guangdong province, China. It's a southmost province, very close to Hong Kong. I'm also a senior research consultant at Atniva Labs. So I work with them in industrial problems, so especially machine vision problems. I work with them. And I'm the former head of the Department of Embedded Systems in VIT, Vellore. I also worked for many years as a design engineer in UK. So I was designing sonar, sound navigation and ranging equipments, and remotely operating vehicles. So that's about a very short introduction about me. Okay. So we start the first slide. It's about computer vision. So as you see, computer vision, it's an interdependent field where you have various other fields getting into this. So you got signal processing, pattern recognition, artificial intelligence, image processing. So you have a kind of, all these fields put across, and they all come across to help you develop a new field called the computer vision. So I was trying to find out a definition for it, and it said it's an independent, it's an interdisciplinary field that deals how computers can be used to gain high-level knowledge from digital images and videos. So you try to derive some information from digital images and videos. So if you are able to do that, and that particular field is called as the computer vision. And from the engineering perspective, you can also think like that, something which can simplify the task a human visual system can do. If you're able to do that, then you can call that as also a computer vision application. And with the advent of the deep learning, the machine learning, and all that stuff, computer vision was booming like anything. So the last 10 years, you might see so much of algorithms have been developed, especially for this computer vision techniques. Okay. So the computer vision tasks. So computer vision started off with the concept called image classification. So people just started off with a simple, very simple task called the image classification. So what we expect the algorithm to do is, you train the system. Say, let us take a supervised technique. So you might be learning or knowing about the supervised learning, where you have an input sample, you got an input and its corresponding ground truth. Okay, so let us see the corresponding ground truth. Let it be the labels. I call them as the predefined labels. Say dog, cat, car, and truck. So you give equivalent images, and what you do is you train the system. So once that system becomes generalized, what you expect the system to give is, when you give a query image, suppose I give a query image, so this is an image I give it to the system, you expect the system to respond it as a cat. Say it's an image of a cat, you expect the system to respond it by saying that is the cat. This is a very basic computer vision task which was first developed. It's called the image classification. Then slowly the task moved to the next step, where you call up classification plus localization. So this is the second thing that started off. What people are doing here is, they know there is this particular image is a cat, but they wanted to localize, which means find out where this cat is, where in this image. So the moment they found out which particular pixels or regions belong to that cat, they drew a bounding box on top of it and said, okay, this particular region belongs to the cat. And this is called as localization. So first it was image classification. Then slowly it moved to what is called as localization, where you draw a bounding box on top of the object of interest. So classification plus localization, and then computer vision slowly moved into a next level called as the object detection. So basically there were multiple objects, 1, 2, 3. There were 3 different objects, and all you have to do is draw a bounding box on top of these objects and classify them. Say for example, dog, car, and cat, and all these regions of pixels, you call them belong to the dog, this one belongs to the bicycle, and this one belongs to the car. But if you look closely among these 3 tasks, what you can understand here is these tasks work on regions. They are region based. So you don't go deeper inside it and say which particular pixel belongs to a car or a dog or a bicycle. All you do is you just draw a bounding box and say these regions belong to car, dog, or bicycle. So then it slowly moved on to a next level called a segmentation. So in segmentation, it was different. What you do here is you try to label each and every pixel with its corresponding class label. So this is more like a fine grain. You go into a fine grain, you use the word fine grain, where you go deeper and deeper and deeper, and you start to look at each and every pixel. So this is an example of a medical image segmentation, where the doctor says, okay, this is the ground truth, and I expect you to segment it properly like this. And the doctor says, okay, there is a lesion here. Can you just show me that lesion? So we need to give an output like this. So what we are doing here is, instead of working on a course level classification, we go deeper and deeper and deeper, and we do a pixel level classification. So here you can see the people here, the backgrounds, the roof, the floor, here the trees, okay, the beach, okay, whatever the lake and all that stuff here. So what you are doing here is you're working on each and every pixel and you're trying to classify them. So now if you have follow it, image classification, then it moved from classification to localization, localization to object detection, and you add a more finer grain, which is segmentation. Now this segmentation has got 2 different types. One you call it as the semantic segmentation. This is a very basic segmentation which most of the medical fraternity will be using it. If you work on medical images, you probably use the word semantic segmentation. So what you do is you got this huge image. All you have to do is classify which is foreground and which is background. You can also call it as a binary classification or binary segmentation. Sorry. You can put the word binary segmentation. Then you can go a bit deeper in that. You also have something called instant segmentation. The same object repeats itself many times, and you try to find out how many instances of these are available in that. All of these are foreground, but you find out the instances of these foregrounds, and you call them as the instant segmentation. This is one step ahead of the semantic segmentation, where you classify each and every pixel, and then you do how many times these pixels are available or came into the image. That's called the instant segmentation. So now we go next step. If you want to look into how the semantic segmentation and the instant segmentation looks like, it's this. Here you have the person and the background. This is foreground and this is background. This is called semantic segmentation. Then you have the foreground with different instances of the person as well as the background, and this is called as the instant segmentation. Normally in medical images we just use these 2 things, but in real world images you also have this one. This is basically for natural images, where you start working on multi-class segmentation, where you want to say this is a person, this is the wall, this is the ceiling, table, and all that stuff. But this is more for a natural images. For medical images, mostly it will be towards semantic segmentation, where you try to detect a lesion as close as possible to the ground truth annotated by the doctors. Okay. So with this in mind, I'll just quickly go into some of the pointers that we need to know about segmentation. In the segmentation, what we expect the output is not a bounding box. You are not just drawing a bounding box over a region. We are not doing that. This is not segmentation. What we expect here is called as dense prediction. We expect each and every pixel of this particular region to give 0 or 1 if we take in semantic segmentation. So that is basically what we are expecting from a segmentation model should do. And the last one, which I have marked in red, is very important. Output should be typically the same resolution as the input image. That is one of the key requirements of any segmentation algorithm. So you expect the output to have the same resolution as the input. Okay. With this, we go into the next slide. Some applications. I'm just showing you some applications. If you just search on the internet like semantic segmentation applications, you will find most of these. So we'll be concentrating about the medical image diagnostics. So here, I think they are finding out the liquid in this image. So you can see this one. Here they are trying to find out or differentiate the shadows from the trees from aerial images. So you can use them for agriculture as well. So you can try to find out where the trees, suppose you want to water the trees, or you put some kind of, disinfectants or something like that, you can put it on from the aerial images. And this is also applicable in autonomous vehicles. Okay, fine. Summary number 1. So I started off with this computer vision. I spoke about computer vision. So how it started off: classification plus localization, then object detection, and then it went into segmentation. Then I told you what are the important pointers about the segmentation. Types of segmentation: you had semantic segmentation as well as the instance segmentation, and some facts about the segmentation. And one of the important factors about is the resolution, which is expected to be at the same size as the input. Okay. So keeping in mind, we'll go to the next one about deep learning for segmentation. Okay. So everybody must have heard about this word called deep learning, or at least the word CNN. CNN stands for the convolutional neural network. Okay. Now the question is, what is the difference between machine learning and deep learning? So if you just do a Google on this, and if you click on if you just Google, and if you just click images of it, you will find this very beautiful, interesting image. I don't know how many of you have seen this image. This one clearly explains what is deep learning and what is machine learning. Okay. So let us take, for example, you are being asked to classify a lift, whether it is car or not a car. Okay. So in the machine learning concept, what you do is, here is the input, and let us take this is kind of a classification stage. Let us take this as an ANN, an artificial neural network. So what you need to do in a machine learning aspect is, there are somebody sits in between this image and the classifier. His job is to extract features. So what you call this as handcrafted features. The people use the word handcrafted features, which means you design the features which best represents the object. If the features are good, the accuracy of the system improves. If the features are bad, the accuracy of the system falls off. So this is the accuracy. So this is the difference, Here there is somebody sitting here. Maybe it's a person who has to extract the features and feed it to the neural network to give you a better accuracy. Whereas in deep learning, what you do is, this whole part is belongs to the deep learning. So This one is called as the CNN, the convolutional neural network, where you use convolutions, a layer of different convolutions with kernels, randomized kernels. You got random kernels here, or filter coefficients here. All they do is extract edges or features. So all you need to do is give the image to this deep learning network. The convolutions run across those images. They extract the features and they give it to the fully connected network. So this is the fully connected network of the deep learning. This is basically the fully connected network, FCN. You can see it on any deep learning network. So the feature extraction and the classification part are joined together in deep learning. So you don't require this feature extraction stage at all. All you have to pass it is into this deep learning network, and that gives you the outputs. That's the reason people sometimes tell deep learning is a black box. You probably don't know what's happening in that. And there is a big research going on into how to understand what's happening within this black box. So many people just give the input images, get the accuracy, do some changes in the deep learning model and get you an accuracy. That's also possible. Now, let us go deeper into this CNN architecture, maybe the feature extraction architecture. As I told you, CNN stands for the convolutional neural networks. So this is a set of images, and you have a layer of convolution here. Yeah, these are basically, you can call them as kernels. A kernel is basically some filter coefficients, and these filter coefficients are randomly initialized based on the normal distribution. So these images get convolved with these convolutions, and you get a feature map. You get feature maps here, and these feature maps go into a layer called the rectification layer. I didn't show you that. That's rectification. Okay, rectification layer. Normally it is like, it allows certain things. Say for example, you have a rectification layer called the ReLU layer. What it does, it stops any value below 0 and it allows values above 0 to pass through. So in this place, you have a kind of, a rectification unit which looks like this. So it becomes 0, it becomes like this. So any value above 0 passes through the next layer. Any value below 0 just stops here. So that's called the rectification layer. And you can change it. You can have sigmoid, you can have tan sigmoid. So many different rectification functions are there. You can use that. Okay. So that is in between the convolution layer and the pooling layer. Then you have what is called as a pooling layer. What is this pooling layer's job is to extract the important features. What are the best features that come out from these feature maps? It tries to extract them and pass it to the next layer. So this is basically an hierarchical learning. So you got layer 1, and again the same thing repeats here, the layer 2, and likewise you can have some dense layers, layer 3, and go on and layer it. So these layers, what they do is they extract the features. Okay, and finally the features are passed into your fully connected network here, and they give you a score. A score is given to you, and based on the score you say whether it is 1, 0 or multi-class representation. You can do that. Okay, so this is a very basic, CNN architecture. You've got different architectures. You've got ResNet, you've got DenseNet, you've got so many different architectures. But this is a very basic understanding of a CNN. It has got an input, a convolutional layer which extracts the features for you. Then you've got a rectification layer which gives you, which removes the bad ones and pushes the good ones. Then the pooling layer, which picks out the best features and it passes on to the next and next layers. So if you see here, this is what happens in the convolution operation. So you can see this is the input. So it has got 3 different, say 0, 1, 2. So it has got 3 different, let us call it like RGB. And you run across a small kernel. This is a 3 by 3 kernel. So you run across this kernel on top of the image. And as it runs across this image, you extract some kind of outputs. So these are basically features. So certain terms that you need to know. What this word called receptive field. The blue region which covers the input image is called the receptive field. That is the field the kernel is looking at to extract the information. It is also called as the context information. So you can see, if you read some papers, you will come across this word, receptive field. It is nothing but the field at which the convolution sees it. So in this case, it's a 3 by 3. The blue region as it passes through is your receptive field. And you can see here some of the features that is extracted here. So this is one from one of my papers here. So we wanted to see what information you get through. So this has got, layer 1, layer 2, layer 3, layer 4. So it has got 4 different layers, and we took a small face as an input. Okay. So in the first layer, you can see that the contours of the face are visible. Can you see that? The eyes, nose, and all that stuff. So there are 2 different convolutions happening here. So you can see these 2 different convolutions give you different contours here. So we call this as a global information. But as this global information features are passed on to the next and next layers, what happens is you try to get into dense features or dense layers or more finer informations are getting. So this convolution layer gives you features which are really relevant to your input image, and you use those features to do some classification. Okay. Now we come to the next one, which is called as the pooling operation. And if you look closely, you got average pooling as well. Okay, but mostly people use this called max pooling or maximum pooling. What is this idea of this pooling operation? Is to retain the important features from a small region and throw out the irrelevant features. You don't want anything which doesn't make any sense, which doesn't add to the value. So what happens is here, it's a 4 by 4 image. So you run across a 2 cross 2 pooling with a side of 2, you can see. So what happens, it just breaks the image into 2 by 2, and it looks what is the maximum value here. So here it is 6, here it is 8, and 4 and 7. So pooling operation actually picks up the maximum values in the case of maximum pooling and throws off the other irrelevant values, and these pooled features pass it to the next CNN layer. So they move to the next CNN layers. There is one big problem with this. So what happens is, at each pooling operation, the feature size reduces. So here it is 4 by 4. So after this pooling operation, this becomes 2 by 2, isn't it? And you can call this as a downsampling operation as well. So from 4 by 4, it becomes 2 by 2. And if you look at any CNN network, this is a typical a CNN model. I just took it from the internet. You can have a look here. Say what happens is an image, as it passes through this CNN network, the size, the width, and the height, they start to get reduced. You can see, for a typical CNN model, the height and the width of the image gradually reduces. This is due to the downsampling performed by the pooling operation. What happens is you tend to improve the number of convolutions. The convolutions, which is basically the depth, which means you extract more and more features, and features from a larger receptive field. Because earlier, this 7 was at 32 by 32, but now it becomes 14 by 14, 10 by 10, 5 by 5. But the kernel size remains the same. So you look in from a larger receptive field, so you extract more and more information. So generally what happens is, the image size decreases while the number of convolution layers convolutions per layer increases. And by doing that, you extract more and more information about that particular image. But there is one big problem here. The problem is this. This is very, very important if you're working on segmentation. Please note down the downsampling operation or the downsampling problem. The model understands, so as it goes from the top to this way, right to left, it understands what is present in the image. Say, for example, this is a number 7. It understands it, but it loses where it is present, which means it loses the spatial location of 7. In this case, example, where the 7 is present, it loses it. And since segmentation, we are working on per pixel classification. The where information, where it is present, is mainly important. Say, for example, you are working on diagnostic of a cancer or a lesion. You need to pinpoint and show where this lesion is present in that image. You can say it is a lesion in a CNN, but if you lose where that lesion is present in the whole image, it doesn't make sense if you're working on segmentation. So this is a big problem with any normal segmentation. And I don't know, many of you probably know, or if you don't know, this is Gregory Hilton. They call him as the father of AI. So he said in one of his meetings, he said, the pooling operation used in a convolutional neural network is a big mistake. And the fact that it works so well is a disaster. He said that. And what happens is, if you're working on a semantic segmentation or any type of segmentation, we require this where information in addition to what information. And hence, we need to upsample whatever is being downsampled. If something has been downsampled, we have to find a way to upsample it so that you also have the where information. Okay. Now, summary 2. We started off with one slide which explains about deep learning and machine learning. It's a very simple thing. Machine learning, you require handcrafted features. Okay. And deep learning, you don't require those features. The network itself gives you the features and it trains the system for classification. Then I explained to you about the basics in architecture. I think it's a very basic, very briefly I told you about what does the convolutional layers do. They extract features for you, and these features are passed into different stages for hierarchical learning. I also told you about the pooling layer, which is basically the max pooling layer. They extract the important features and pass it to the next layer. And I told you one of the biggest problems with the max pooling with relevant to segmentation is you lose the where information, but you gain the what information. You gain the what information, but you lose the where information. And if you're working on segmentation, you require this where information. Segmentation part, you require this where information. And for that, you definitely need to upsample things that have been downsampled by the pooling layer. Okay, fine. We go into the next part is how to solve this CNN problem using an architecture which is referred as the UNet. Okay, now this is probably you might have heard about this word called UNet. It's a UNet because it has got a shape of a U. Okay, and it's been there for many years, maybe at least like 5 or 6 years. It's been there, and it's mainly for medical image segmentation. Okay, if you look into our biomedical segmentation, if you look here, it is mainly used for this, and you can say look in for so many variants of this. And in a hard group, we are designed like 3 or 4 variants of this, and I will be explaining 2 of that in detail today. Okay. So I told you the problem of a CNN architecture. Then people started applying different upsampling techniques. And I told you upsampling is one of the main requirements for the segmentation. And there are various ways by which upsampling. So you can use a traditional, bilinear interpolation, those kind of interpolation techniques as well, bilinear, bicubic. There are so many different or transpose convolution. These are techniques by which you can, upsample or interpolate it. But there was one person by name Olaf Ronneberg. Okay, so he was a professor from the Freiburg University in Germany. So that team developed architecture called the UNet. Okay. So you can have a look at this. This is the UNet architecture. Okay. So what happened is this is has got a shape. People use it as V network as well, but he called it as U, so I will also call it as UNet. Okay. So what happens is it has got two different pipelines. Let us call it as pipelines. This pipeline this way, and another pipeline this way, and you can call it as a small tube here. This tube connects the forward pipeline with the backward pipeline. So we call this forward pipeline as the encoder and this other pipeline as the decoder. This forward pass is very similar to the CNN, which means you start at this image, you give an input to this image, and what you do is these blue ones are the feature maps. Okay, let us call this as the feature maps, and these orange ones are basically a 3x3. By default, you was using only 3x3 convolutions, and a ReLU layer basically removes all the things that is below 0. Okay, so you can see here he was using like 1, 2, 3, 4 different layers. So you can see the feature map size getting reduced, the depth getting increased. Can you see that? Yeah. And what happens is at this stage is basically called, it's a very similar to your CNN architecture. You get what information here, and then you pass this what information to another opposite pipeline here, a pipeline which has got these yellow ones, which are called as upsampling ones. So these are also called as the deconvolution operators. You can look into for fractionally strided convolutions. If you are more interested, there is a word called fractionally strided convolutions. You can look into that. So what this thing is doing is, it is just blowing up or zooming up whatever information is coming here. It is zooming up and giving you an image, a segmented image, which has got the same resolution as the input. So this is what in the last segmentation pointer, I marked something in red. I said the segmentation output should be of the same size as the input. And here, with this UNet, you can actually get back the segmentation outputs, which are of the same size as the input. And this is achieved by two things. One is the upsampling, and there is another one, which is the green things here. These are called the skip and copy connections. What it means is, at different layers, what they do is they take some features from here. So this is layer 1. Let us say layer 1 here, layer 1 here. At this point, what they do is they take some of the features from here and put it to the decoder side here. They concatenate, and then they apply two different convolutions here. Similar thing happens here. So at layer 2, from the encoder side, they copy some features into the decoder and they apply two convolutions. And likewise, when they are doing it, they're able to get precise spatial resolution of the segmented output, and also the segmented output were having the same resolution as the input image. So if you want to look at some of the important pointers about this, it starts like this. One is the encoder. Basically, what happens, it's the same as the CNN, which means the image resolution reduces, the number of filters improves, which means number of features get increased, or the depth increases, and this is very similar to your forward CNN. Whereas the decoder is opposite to the CNN. It blows up the image. The image size gradually increases as it passes through each and every layers of your decoder network. And these 2 points are important. To get precise location at every step of the decoder unit, they use what is called the skip connections. What they do is they take out from features from the encoder side, they copy it into the decoder side and after the concatenation, they apply two regular convolutions to assemble to a precise output. So this is how unit works. Very simple. Two different pipelines. One gives you what information, other one gives you where information. The where information is achieved by two things. One is upsampling and another one through skip connections. So this is what happens. Input to the encoder, height and weight get reduced, which enables the filters to look deeper into the network and focus on the receptive field. And encoder to the decoder chain, they improve the height and width. Skip connections help them to get precise locations, and you get where information at this point of the pipeline between the decoder side. In the encoder side, you get the what information. Now, for the segmentation point of view, I said you require these two things, and unit helps us to achieve these two things: the what information as well as the where information as well. Fine. So to test this, whether it was actually working, so I, along with some of my master's students, we started investigating this unit architecture. So what we did is we had wanted to work. So we were basically work on this ultrasound images. Okay. So we work on this ultrasound images, and so this is some of the ultrasound images. So this was given to us from the. So this is breast ultrasound images. Yeah. So you can see a lesion in this particular breast, and this is the mask given to us by the doctors. So normally the doctors give us the mask. So the mask tells us the shape of this particular lesion, and this shape is very important. Say for example, if it is a regular shape, then it could be a benign cancer or a benign lesion. If it is a complicated shape, then probably the doctor assesses it and says that it could be a malignant lesion. So the shape is very, very important here. Yeah. So what they did is we trained like about 2,000 samples and ran across different epochs, and we took up at the outputs at each stage of the unit. So this is the first thing, the encoder section here. This was the size we used. This was 16 different convolutions, and we had about 16 like there are too many tunable parameters with it. So these were the 16 different feature maps that were generated. So you can see the lesions coming out. Can you see that? So this is the outputs of different combinations of filter kernels. So different random kernels come into it. They interact with the image and give you a different feature vector or a feature map. And what happens is the next stage, the next stage right now it is 512. Just look at the 512, and your lesion is something like something, let us say 350 or something like that location. Now what happens is the next stage I told you, it's a rectification layer where we remove anything below 0. So this happens. So any value below 0 is removed, and this is again the feature maps. Yeah, you can see the feature maps here. These are the feature maps, and the lesion is quite visible. You can see it here. And the next stage is the output of the max pooling. This is what happens. So output of the max pooling, what happens? Earlier it becomes 512. Now it becomes 256. It becomes half of it, but still you can see the lesions of it. So only the best features are preserved here, but the where information has moved. So earlier it was like 350. Now it has moved like what do you call, say something like 175 or something. It has moved. The locations moves and moves. Now this feature map is passed on to the next one. So now again, instead of 16 different feature maps, you have 32 different feature maps here. So I can't show all the things. I just showed you 16 of them, but still you can see the lesions coming out here, but the locations are changed. But if you also noted on this one, this is the tunable parameters, which means the number of the number of parameters that the system has to tune gets increases, which means you have to generalize a lot on this. Okay. Now from 256, it went to 128. Still lesion is visible. Earlier lesion was visible here, but now you can't see the lesion. Now again, some visibility is here, and you lose it. The visibility loses. Then 64, what happened? Yeah, 64 becomes 32 with 265, 265 different feature maps. I think you have all the 265 feature maps, and you can still see the lesions here. I believe you can see it there, but the position of the lesions has greatly changed. Earlier it was something like 350. Now I'm unable to show, but maybe it is like I don't know, maybe it's 32 means something like 16 or 18 or something. The position of the lesion has changed quite a lot, which means you've lost the bad information completely, but you have gained the what information. The lesion is present, you're able to gain it, but you lost the bad information. Now this feature is fed into the decoder network again. So a decoder network, which means I take some information from the encoder part, I concatenate with it and apply a convolution. And you can see from 32 to 64, the feature map starts to come up very well. And as I increase it, you can see the feature maps and the lesions, they tend to show up far better and better, and they start to get back to the original location where it was. You can see here. So now you go to the last stage here, the final output of the decoder. You can see you're able to reconstruct it back to the same resolution with the shape coming out. So you got the shape of this particular lesion is visible, and you also have the location as well. The location information is also preserved, sorry. So you also preserve the location of that particular lesion. And finally, when you compare it, you basically do a comparison with this. So this is the input image, this is the mask given by the doctor, and this is the output that is generated. And you can see the black one that is drawn on top of this, that is the actual ground truth given by the doctor, and this is what we have predicted from our network. Okay. So this is some of the trials we did, and we wanted to examine and analyze how the unit works, and we are able to give you a proper analysis on this. Okay. Now summary 3. I explained to you in a very brief manner how the unit works. I think if you want to have more understanding, you can refer to so many papers about this. There are so many papers, what you call codes are available on the GitHub. You can look into that. And I told you about some pointers about unit, how they improve the upsampling. That's what some of the pointers. And I showed you, maybe you won't get this opportunity to look into each and every stage of that encoder decoder pipeline, how it happens. I showed you those results as well. Taking the encoder separately, what happens at each and every stage of the pipeline, and also I showed you the decoder side, what happens at each and every stage of the pipeline, and how you get both what information as well as the bad information. So with this, we finish off summary 3 of that. Okay. Now we go into the next one, which is my contribution, my lab's contribution. So we called it as the hybrid unit models because we started adding bits and pieces from other networks so that we can have a better segmentation result. So we call this as the hybrid unit models. So we designed like 3 or 4 models we designed, but I will explain you 2 models today, but you're most welcome to refer to my publications. Yeah, fine. The first model, we call this as the RDA unit. Okay, it's the residual dilated attention gate unit model. So it was published in PLOS One. It's an open source. You can refer to this. Yeah, fine. So we kept the shape of this particular unit. The architecture remains the same, but there are a couple of modifications. The first modification is with respect to these parts. Okay, what we did is we never used the normal CNN architecture. We used what is called the residual networks or resonance. The need for ResNet is there is a problem called vanishing gradient. And if you just go deeper into this network, so people think that if you have more layers, it means more and more dense features. But in reality, it doesn't happen like that, because the network trains by the error that is getting back propagated. If you have deeper networks, the error is very minimum, and what happens? The network saturates. So to avoid this problem, we went in used what is called as residual networks, and we replaced each of these CNNs with ResNets. That is one thing we additionally did. The second concept we did is, I told you, this pipeline, this is a tube I explained to you, a tube which connects the encoder and the decoder chain. So what we did is, we introduced a concept called dilation convolution. So this dilation convolution improves the receptive field. So normally you might have seen convolutions where the kernel slides within what a step size of 1. But we gave different step sizes so that we can see a bigger area of the image or the feature map. Let us see, like, bigger receptive field. Then we went into the other one, which is this part. We didn't actually just take those things from the encoder, or take those things, the features on the encoder, and concatenate the decoder. What we did is, we went into this national, I think NPL, natural language processing, NLP, yeah. Okay, we went in that and we took up some concepts like, attention gate, and we replaced this attention gate models in that skip connection. So what these did is, they had a learning ability to focus more on the foreground rather than on the background. So we employed these three different novelties in the existing unit architecture, and we called it as the RDA unit architecture. And this is what it is. This is the traditional unit, and we replaced it with residual network, attention gate, dilation convolutions. And this is the example of a residual network, how it works. This is the normal CNN. The residual CNN, to avoid this vanishing gradient problem, you have this pass, which is basically the normal CNN. Along with this, you add up with the input image or the input feature. So suppose your gradient is going to be 1.1. When you add up with this feature, it becomes 1 plus. So the error is always positive here, or it has got some kind of a positive value. So the network was training better in this case. That's the reason people go in for residual networks, ResNets. The second thing is, as I told you, the attention gate modules. This is from the encoder output. This is from this lower layer of the decoder. So we pass it through a couple of filters. Then again we do rectification, and then what we do is some more filtering operations are carried on here, and finally we select the best features here, which means we apply a sigmoidal sigmoidal transition function here to select the best features and focus on the foreground here and remove the background. So likewise, we are able to get more better concatenation of features from the encoder to the decoder. And finally, this one is the dilation convolution. And if you want to understand better about dilation convolution, this is a sliding here. So this is your normal convolution. Okay. This is may put stride rate L is equal to 1. So you move it with every pixel. Now this is a dilation convolution with a dilation rate of 2, which means you can see the kernel is spread out. What we have done is we introduced zeros in between those coefficients. So earlier, if it is like 1, 2, 3, what we did is we introduced zeros here. So now what happens is the connectivity remains the same, but you have extra redundant value. It doesn't matter. All you are looking here is a bigger receptive field, which means you have more information. Similarly, here you can see a dilation convolution of a rate of 3, which means you got a better receptive field. You look more deeper and deeper and get more information here. So this is one novelty we added to that particular unit, and I'll show you some outputs here. So this is all our data sets here. We took some data sets from the Netherlands University Hospital. So we use them for training and validation. And we had a couple of our own data sets from the hospital. And this is another one from, it's called dataset P, which is, I think, if you want, you can use this. This is freely available. You just need to kind of request to this person and he sends you the data set. So we use these two to test our network. Okay. Now, this is the output of our network. So this is the ground truth. This is the images. I think these are test images. And this is the ground truth annotated by the doctors. And this is our result, RDA unit result. Okay. And what we did is we also compared it with other networks as well. So we compared it with like 13 other networks here. So I can't really tell you. You can just read it here. Segnet unit. So you can like 13 or 12 different units, architectures we compared here. I think this is 1, 1,2. This 1,2 matrix is our result here. This is our result. This is our result. And you can see the results of other segmentation algorithms as well. You can see here. And you can also see at this point of time as well. So this is basically a malignant cancer, So which is you can see the shapes are irregular, a very complex shape, and you expect the shape to be taken out perfectly. If the shapes are wrong, the doctors cannot predict it properly. So segmentation is really important here. And we also did a quantitative analysis, which means numbers. We want some numbers here. And this one stands for the mean intersection of union, which is also called as Jaccard matrix. You can look into that. And the F-score, dissimilarity coefficient. So apart from few different things, like these ones, for the majority, our network was doing very well. So it like say accuracy was like 97%. But in machine learning, you don't look into in accuracy. You look into the F-score, and for segmentation, you look into the dissimilarity coefficient or the mean MOU. So ours is like 85% overlapping with the ground truth. That's what it says. The dissimilarity coefficient or the mean IOU says that we can have about 80% similarity with the ground truth. What doctors have said, ours is actually 80% similar to that. So that's one of the results we have, and we compared it with other segmentation models as well. I think you can look into the codes available on the GitHub. Yeah. So I got the next one, which is called as the RadioNet WGAN. This is the RadioNet we developed, and we also went into this adversarial learning, which is the GAN network, and this was the time. This is a new loss function which is being used. I think it's already available. We try to use it in our network and try to segment it in a better way. Okay. The general idea of GAN, probably it's one of the new research areas or the hot research areas of GAN. So you got patch GAN, pixel GAN. There's so many GANs available. The general idea is it has got two different architectures. One is the discriminator and the generator. And it's got adversarial learning, which means they compete with each other. This generator and the discriminator, they compete with each other. So the input normally, what happens, it's noise. And this generator tries to give you some fake images, whereas the discriminator is trained with real images. So the discriminator's job is to find out if there is a fake image or not. The discriminator finds out the fake images, the generator is updated. The generator is able to fool the discriminator is updated. That's how it just works by like that. Okay. So what we did is instead of noise here, we trained our network, our ground truth results here. We just took the bus images along with the ground truth. We trained the generator and the discriminator with our data set. And what we did is, when we trained it, the generator, we used the rad unit. You can see here, we just used our RDA unit here. So we used RDA unit as the generator here. And this was generating the segmentation outputs. And this segmentation output was passed on to the discriminator. The discriminator could be any CNN. It's just going to say 1 or 0. So you don't require a unit architecture. You can have a generalized, a normal feed-forward CNN architecture. That's enough for that. So with this architecture too, we did some segmentation and we compared our results as well. So, and yeah, this is one thing. You can see how it works. So this is the bus image, the ground truth given by the doctor, and this is actually the overlaid one. So at each cycle, which means generator and discriminator compete with each other, the blue thing, the blue output comes out from the generator. What happens is, this is the overlap. The purple is the overlap between the ground truth and the one that is predicted by the generator. So as it passes across, so here in this case, the discriminator has 1. But as it passes through different iterations or different cycles, eventually the generator understands and it starts to predict some good segmentation outputs which are able to be closer to the ground truth and fool the discriminator. So you can see here. So we took up some various cycles here and we plotted those outputs here, and you can see how the discriminator actually and generator compete with each other to give you a better segmentation output. So again, we compared it with the different models, and ours was something better. It was slightly better than the RDA unit, and this is the WGAN, and we were able to 0.86 and 0.89, say about 0.03% improvement in terms of F score. It was quite good. You can refer to this code. This student was my internship student. She was here. She was working with me. So you can refer to this GitHub. You can just request her. She would be able to send you the code as well. Okay. So this is about our unit models and deep learning concepts for segmentation. And again, summary 4, as I told you, I spoke about 2 different models here. RDA unit and RDA unit WGAN. Both were developed by us in our lab. I compared this performance with different architectures, and we also were able to show our network was far better than other existing networks. So this comes to summary 4. Then I'm going into the next one, which is the additional things which I thought of talking to you. Okay. This is feature-based. Earlier I was speaking to you, machine learning. Machine learning. I was speaking to you about machine learning, where you require to extract handcrafted features. So I will explain you one of the one of our papers where we used features, basically shape and intensity features or gray level features. We extracted it to do a fundus image segment or retinal image segmentation. So it's again published in PLOS One, so you can refer to it. It has got a very high H index, this journal, so you can refer to this. Yeah. Okay. So this was the entire block diagram of our system. I will tell you our contributions. So this is our contribution. This part is going to be our contribution, whereas this one and this one are from the existing papers, because if you look into the fundus images, the pre-processing step remains the same. You have to pick out the green channel, remove the light reflex, all these things are same. So we just use their pre-processing, but we added our own contribution to this. Okay. So these are the pre-processing techniques. The first one is green channel. I think you can refer to this paper. I can't get in deeper into this because of the timings, because this itself is a huge paper. All we do is we extract gray level features, which is basically the intensity features, and we also have this image, which is called as the Bessel enhanced image. This is the image here. With this image, what we do is we extract shape features. For shape features, we use Zernike moments. So I've been working on Zernike moments for quite some time with biometrics and other stuff. So I applied the Zernike moments for extracting shapes in retinal images. So this is the gray level features. So 5 different gray level features you can extract it. So we followed that paper called Marin et al. You can look into that paper. We just used their equations and we were able to extract all these 5 different gray level features. And then we went into the shape features. Now what this shape feature means is, as you vary the polynomial, the Zernike polynomial, you tend to get different feature maps. And as you run across the image using a sliding window technique, you get each and every pixel mapped to a feature map. So in this case, you've got 36 different feature maps here. You can see here. And each of these 36 are unique feature maps. And what we did is, we found out certain things in that. You can refer to my paper there. And what we did is, we selected the training points. So because these are shape parameters, so we are very particular in handcrafting and carefully selecting the veins and carefully selecting those regions, which are ones and zeros. So these ones are zero. We don't require this. So we need to remove this. So we classically selected this optical disc and those kind of stuff. And we made them as zeros. And then we trained a simple ANN network. So when we trained it, we were able to get a nice segmentation of these retinal scans here. You can see here. So all the 20 different from the tribe data set. We also did it for the star data set as well. And we compared to this. So this is the paper you can check out. This is a very good paper, Marin et al. The transaction paper, you can look at that. So ours was slightly better than that paper in terms of, and ours are more generalized. Okay. Very slightly better than that, their paper. Okay. So till now, I think I finished off with deep learning, machine learning in terms of segmentation, explained to you one of those machine learning segmentations, and shown you some outputs from our papers, and given you some other suggestions as well. And finally, this is quite interesting here. Yeah, aiding diagnostics. So our research group, we do segmentations and all that stuff. We publish papers, but we also work closely with industries, especially the ultrasound industries. And we also work with doctors from the Shantou first affiliated hospital. So we closely work with them. And we always want to help them in diagnosing. So earlier I showed you segmentation, but from the research point of view, it looks nice. But what is the take from this is something which I would like to explain here. Okay. So you might have seen the normal ultrasound where you go to the, where you go down to the hospital, where the physician just puts up a probe on top of you, and the ultrasound image comes in. There's something called automated whole breast ultrasound imaging. So we work with an institution which is basically develops ultrasound equipments. It's called the SIUI, Shantou Institution of Ultrasound Imaging. And they have developed this automated whole breast ultrasound imaging. You can see here, I'm just going to play this video. Let me see. Okay, now it should be, yeah. So, can you see the video being played? Okay. So, this is different from your normal ultrasound because the transducer, without any help of a physician or anybody, a person, it moves on top of your breast and it gives you the scans, which means the transducer gives you X along the X-axis and along the D-axis, it gives you the scans. So now you can see here the transducer moving. Can you see it? Let me show it. Highlighter here. Okay, sorry, it stopped. Let me go back. Yeah, I'm sorry, I can't. Yeah. So now we can see the transducer actually moving across the breast. So So they were having such a kind of equipment, and this is first in the kind, with this SIUI, first in the kind. And what happens is, as it scans, it gives you resolutions of ultrasound maps, which you can see it over here. Okay, and let us wait. Yeah, give me a second. Let us see. Yeah, so you can select that, and I think you can see on this side, you can see the shape of that ultrasound. The image, it passes through this. Now there was a problem here. So they were actually, the scanning direction is this way, and they were happy. Let me turn on my pen. Yeah. So what happens is the scanning direction is this side, and we were getting actually slices like this. So we call this as a sagittal slices. So X to D, let us call it as X and D slices. So this is the one, XD slices, and we were having closely mapped X and D slices. So it was very difficult to doctors to see the entire breast. So they gave us this idea. So they gave it to us. So what we did is, very simple, we stacked it across. So we stacked it, all this stuff in one particular frame, and we cut this along the X and Y directions. We cut this like this. Okay, we cut this. So when you cut this, what happens? You can see the shape comes out very well. And in fact, you can see the lesion, the nipple here. All this stuff was the milk glands. These are the milk glands here. So all this stuff are clearly visible. So once we change from one scanning direction to the other. So this is one of the things we gave it to them, and they were included in that particular, SIUI's ultrasound equipments. This is one of the, it's called the automated whole breast ultrasound imaging, ABUS. You can search on the internet about this. The second one was very, very interesting, and I wish you can have a look at this. So this is again a published paper in a very good journal. So I told you about the ultrasound. I told you about the automated whole breast ultrasound. Now you also, I don't know how many of you know this. This is called as a contrast enhanced ultrasound. It is called as the CEUS. I don't know how many of you have seen this. So if you work in life sciences, you might have seen that. Suppose you want to check if a particular cell is active or not. What happens? The person puts some kind of a contrast agent. So when you put some contrast, say you put some kind of what is called as contrast agent. Contrast agent. He puts it in, and then he looks it into the microscope to see if there is any kind of reflection happening. So those kind of ultrasounds are there, and we also worked on that. And I'll show you. It's very interesting, and we are able to differentiate the benign and the malignant cancer here. So this is the entire architecture. But before going into this, let me show you the video first. Again, I have to come back here. Now, onto your left-hand side is a normal ultrasound video, and onto your right-hand side of each of these, benign and malignant, is the contrast ultrasound video. How do I clear this? Wait a second. Clear all drawing. Okay. Now I'm just going to run the first video onto the left, which is basically the benign. So now this is the ultrasound video has been captured, and the doctor actually sits inside the contrast agent. So as it passes through the regions of interest, the cells respond. See, the doctors told us if it is a benign region, it takes longer time to respond. So it takes, say, for example, here, the passage or the blood perfusion. We call the word blood perfusion, which means the passage of blood through that particular region of interest, and the characteristics that come out. It takes a longer time for the benign cancer. But this is, you can see here, the malignant here. And you can see this particular point. Okay, I'm stopping this, and let us see this side, onto the right-hand side. Can you see the small insertion here? Let me draw it here, if you can. Here. That is basically where they send the agent. Let me come back and erase this. Okay. Now I'm playing this video here, and you can see here, the moment that agent is sent across, you can see something happening here. Immediately, this region will start to activate. Can you see here? Can you see this region here? See how fast it activates. The characteristics, it starts to show its characteristics immediately to that agent. And the the rise time, so it goes up, it shows its characteristics, and it comes down at a very faster rate. So like doing that, what happens, you can see here, within 1 minute, it goes up, 1 minute and 15 seconds, it goes up and comes down. Whereas in this one, it's already like 55 seconds, and you can see here, this is still going on and on and on. It takes a longer time for the benign ones to actually show their characteristics. Whereas the malignant ones, the rise time is very fast, and the fall time is also very fast. So keeping this in mind, we designed a color-coded concept to help the doctors to show whether it is a benign cancer or a malignant cancer, or a malignant, let us say benign lesion or a malignant lesion. And if you now look back here, you will understand it. So the first step of this is to read the videos, it's called the contrast enhanced ultrasound videos. The first step is to stabilize those two blocks, because those are basically running on two different transducers. And this is where we have the information from the doctors, the rise time and the fall time. If it rises very fast, we give a red code to those regions. Say, for example, these regions are rising very, very fast. Whereas the blue regions are the regions which are rising very, very slowly, which are benign regions. So using this, the doctors can, he doesn't need to sit and look at that. You don't need a big experience to do this. All he has to do is send this video to us or to the system. If it is a benign, and we run this inside our algorithm, if it is a malignant cancer, it gives you a better red and responses. If it is going to be a benign cancer, it has got more blue regions. And this is, you can see here, it goes up and down at a very faster scale, and that's how it is. Yeah, and I think yeah, with this, I think I need to end up. Yeah, I think it's almost time. Yeah, 49. Oh my God. Okay. So I think I given some idea about segmentation. I started off with a kind of computer vision, I think. Then I slowly moved into the segmentation. What is segmentation? How it is done? What are the problems with a normal CNN? Why people went into UNet? How we get UNet, both what and where information. And I also explained you various hybrid models, which were, or you can say different variants of units. And I also given you more information about feature-based segmentation, aiding diagnosis, which is all you want from a researcher's point of view. You want the doctors to be helped from your research. And I showed you how our labs do help us. So one is with the ABUS, and another one is with the CUS, contrast enhancement ultrasound videos. So thank you very much, and you're most welcome to ask me any questions, and if you're interested in collaborating, and you can just write to me on this. And before, just give me a quick, I think, this is our group called the Pattern Recognition and Material Intelligence Group, and this is our university, and these are some of my friends who work with that, and we closely work with doctors. We almost have doctors visiting us every week. And the good thing is we take quite a lot of interns from India and from Malaysia, University of Malaysia. So these guys are from VIT, Vellore, and I had couple of students from NIT Tiruchi as well, and from Galgotia as well. Many students came across, and we have a very good lab there. And this is some of the areas which I forgot to mention in the first slide. So I work on these areas: biometrics, affective computing, biomedical signal and image processing. This is my PhD area, and I still work on this. Depth estimation. Three main things: deep learning, machine learning, and FPGA implementations is also one of my core areas of research. So with this slide, I thank you all for your patient listening, and I'll go back to the slides. And if you want, you can ask me any questions. Thank you very much.
Sir, good morning. Good morning, Professor. Can you please share me your email ID again?
Okay, here. Yeah. That's there. jalexnoel@stu.edu.cn. And you can also look into my ResearchGate. Yeah. You just search my name, probably you get some information about me. Okay, so should I come out of this? How do I come out of this? Yeah, okay, fine. So you can ask me questions if you want. And
Sir, is it possible, like, can you collaborate with us for some DST projects if you are planning to send, like, India-Chinese collaborative bilateral research projects?
Yeah,
can you help us?
Yeah,
okay.
Absolutely. I've written with Paila. I think BRICS is always there.
Okay, so my name is Dr. Kollabana Prakash. I am from KL University. So just remind me, sir. Please remember.
Yeah, just
okay, I will send you a mail. I will send you a mail.
Yeah.
Thank you very much, Professor.
Yeah.
Sir, there are few questions in chat.
Oh my God, there are so many questions here.
By
okay,
Sandeep.
I don't see that. Oh, sorry.
Yeah, no issues, no issues. This is by Sandeep Kumar.
Just let me have some water.
Yeah. So the first question is like, is it possible to know the features selected by deep learning models?
Well, that's what I told you. Deep learning is a black box. So deep learning is basically a bigger black box, and the features are extracted by convolution. Okay. Those convolutions are done through kernels, which are randomly initialized. Okay. So when it is randomly initialized, we actually don't know what sort of features that come out. That's the reason you have various other stages to pick out the best feature. I tried to do one paper called ZNet, where I think I can share the paper somewhere. It's called the invariant moment. I forgot. So what we did is we used Zernike analysis inside the convolutions, and we initialized our own feature maps. But I think from my point of view, analyzing deep learning is quite tough. There are big research is going on to understand the black box. So all you can do is look at the features, but how this feature comes is not possible to analyze because they are randomly generated from the kernels which have been randomly initialized. That's my question. Answer for that. Yeah.
Yes, sir. So the next question is like, what are the common software tools that is being used for medical image processing, and what are the hardware requirements to carry out our experimentation?
Common software tools in the sense of what sort of work are they looking at? See,
they're looking for medical image processing.
All we are using is like Python, Keras. These are things we are using, and I don't really have any kind of big equipments to do it. All I have is images. I take the images, I speak with the researchers, I ask them the images. Somebody publishes the papers, I request them to give me the data set. And I just have a couple of works. Okay, if you wanted to do a deep learning, you have to have a nice workstation. Or you have to just rent a workstation out on the online. So I got about 3 or 4 workstations in my lab. So all with equipped with Teslas. So with that, I can run like thousands and 10,000s of images with my students. So from my point of view, medical images, you just require a basic Python code or a MATLAB. You don't require any kind of bigger hardware unless you want to collaborate with some big university industry. All you have to do is search Keras, search Kaggle, Kaggle. There's a book, good website. You can search there, and they give you data sets there. You can just use those data sets to start your your ideas, your applications on the medical imaging. That's my answer. Yeah.
Yes, and you were mentioning about your models, right? Your research work, and there is a question on that whether it can be used for voice matching.
Voice matching, in the sense, see, voice is basically a 1D signal, right? The time varying signal. I am working on a spatial signal, which is not varying in time.
Okay.
So if something is varying in time, you have to look into a different model altogether.
Okay.
Isn't it?
Yes, sir.
Voice is a frequency with respect to time. It's amplitude with respect to time if you work on the time axis. And if it's going to be a frequency, and magnitude if it works, if you look into the frequency axis. Or if you want to work both, you just need to look into the wavelengths. I'm working on spatial images.
Okay.
Yeah. So I don't think it's really relevant to this particular topic at all. Yeah.
Yeah. Okay, sir. And there is one final question in chat, which is how can we decide the number of layers we have to use?
Okay. That's a very good question. I don't think there is any kind of analysis being done. One thing is there is a perception that if you have more number of layers, the network does train well. But what happens, as you know, the network trains by back propagation algorithm, or back propagating the error, which is the gradient of the error, just back propagates through different layers. If the error is actually some value, some substantial value alone, then only your network will train. Suppose you have a huge network and the error is going to be 0.0001. What is the use? And you take a gradient of that. What is the use of having 0.00 error being projected back? Because the network will become stable. It will get saturated. Isn't it?
Yeah.
Yeah. So what happens is people worked on this and they found out that you can, instead of having too many layers, you can just connect the input to the gradient. That's what the residual net came across.
Okay.
So if you look into that concept like bias and variance errors, so if you are able to analyze that bias and variance errors, which says what is the size of the feature is required, what is the size of the what is the feature size, should I increase the feature size or should I increase the number of data sets? If you're able to work out with that thing and keep the layers to the last thing, then probably you have a better good accuracy. So that's from my experience. I won't keep on increasing the layers. I just look into the feature maps. I look into the number of data sets or the number of samples I use in the data sets. The last thing would be my concentration would be the layers.
Okay, fine, sir. Participants, if you have any other questions, you can unmute yourself and you can ask.
Yeah, go ahead. Yeah.
Participants, it is your time to ask questions. If you have anything, you can clarify now. Okay, I think.
Sandeep, your question was something like, sorry, just 1 second, let me. Sandeep,
yeah,
was
yes.
your question like deep learning features selected by deep learning, what can be done? You want to display the feature, well, you can just plot it. You can just print it and see. So it's going to be like a two-dimensional thing. What you just do it, take it as a matrix and then plot it like the way I plotted it. That's all it is. But what happens is that at every iteration, the features will change. You can definitely do it. I thought the question was different. You can display the features selected by the deep learning model. Definitely, you can do that. Yeah. Okay, please go ahead.
Yes,
hello.
sir. Nandakumar. Yeah.
Yeah, sir.
Please.
Sir, it was a very good presentation, sir. I have just question: if I have samples of voice, can I find some kind of pattern or through segmentation by using your methods?
See, that's what patterns of voice in the sense. Are you looking in for a time varying model, or you're looking for a spatial model? That's the question.
Sir,
You have to you have to look into a time varying model, isn't it?
yes, sir.
Yeah, so it will be more like LSTM, LSTM, I think LSTM, right? Well, let me give a quick search. Wait a second. I think there are so many time varying models are available there, which help you to extract what is the frequency content in that particular time. What I'm speaking is a spatial. It has got X and Y axis.
Right, right, sir. So I need to find some models which work on frequency and time.
Yeah. Yours is a time varying signal, so you have to look into the time varying models.
Right, sir. Thank you, sir.
Yeah.
So can we analyze EEG signals with this technique? There's a message in chat.
Yeah. So again, the question is, are they time varying or are they not time varying?
Okay.
So see, normally what people do is they take the EEG signal and they convert it into an image and they train it into the deep learning model. I've seen some papers on that. But my point of view, a signal and an image are two different entities.
Okay.
Okay. Yeah. So signal is basically varying in terms of time. If an image is varying in terms of time, it becomes a video. So I got a different notation because I've seen papers, people just, take the signal, convert them into image and train the neural network or a thing. But I have a different notation. So I say it's not possible to do it. But I have seen papers, people do it. I hope people can understand what I'm saying.
Yes, sir.
Yeah, please. So for that person who asked, it's called long short-term memory, LSTM. You can look into this concept called LSTM. LSTM. Okay.
Thank you, sir. Thank you very much, sir.
Yeah. Any questions?
I think we are done with the questions, sir.
Okay. So can I?
Yeah, yes, sir. Thank you very much for this wonderful session, sir. You have opened up a lot of things here, and you have given broad idea about your research, and probably the participants will try to kindle more knowledge on what you have given us. Thank you so much, sir.
Okay. Thank you very much. Yeah. So thank you very much for inviting me for the session, and thank you for your patience listening. So you listened a lot, I think.
Welcome.